All right, so for this week, we're going to be working on simplifying rational expressions. In fact, some of the expressions we're going to be simplifying are technically not what we would classify as rational expressions, but they are related. And so the techniques that we use are going to be pretty similar. So the purpose of this section is really to help us in the parent class with section 1.2. It's not going to be very helpful for 1.1. It's for 1.2 where we'll be evaluating limits by simplifying algebraic expressions and things like that. So to start with, let's just get right into one of these. I want to simplify this expression, 3x squared plus 14x minus 5 over x plus 5. Okay, so what do we mean when we say simplify a rational expression? Well, we're not going to have like a really strict rule as to what that means, but generally what we're trying to do, at least in one of these types of expressions, is factor anything that can be factored and then cancel anything that can be canceled. That's kind of the general process. So looking at the numerator and denominator, I see that I have a quadratic expression in my numerator. It's possible that we can factor this. Now, there are a bunch of different ways of teaching how to factor quadratics. Being that that's a prerequisite for this course, we're not going to go through all of them. I'm just going to show you the one that I like to use. Sometimes this gets called the diamond method, so you might know it by that name. What we're going to do is we're going to take a look at the leading coefficient, which is 3, and the constant term, which is negative 5, and we're going to multiply those two numbers. That gives us negative 15. Okay? Then I'm going to take the linear coefficient. That's the coefficient on the x term, and I put that down here. In these other two areas, what I'm going to do is put two numbers which will multiply to make negative 15 and add to make 14. So if you kind of go through some trial and error and sort of reason it out, you should fairly quickly arrive at 15 and negative 1. Notice 15 times negative 1 is negative 15. 15 plus negative 1 is 14. So these two numbers satisfy both of those criteria. Most of you probably know up to this point of the diamond method. I do something here that I've not seen a whole lot of algebra teachers teach, so this might be unfamiliar to you, but it's a cool trick. So what I'm going to do is take both of these numbers and I'm going to put them over the leading coefficient of my quadratic, so 3, creating these fractions. If either fraction can be simplified, you simplify it. So 15 thirds is the same thing as 5. However, I kind of want to keep it in the form of a fraction, so I'm going to write 5 over 1. Negative 1/3 can't be simplified. That's as good as it's going to get. Okay, now what I can do is use these two fractions here to factor this, and here's how that works. The first fraction, the denominator, represents the coefficient on my x term, so 1x, or just x. The numerator represents my constant term. It's a positive 5, so I write plus 5. Going over to this fraction, same thing. The denominator represents the coefficient on my x term, so it's 3. That makes 3x. And the numerator is my constant term, negative 1. That is the factored form of that numerator. And you can verify by multiplying it back out again to make sure that it worked. The denominator, x plus 5, is a linear expression, and I can't factor it any further. But if you notice, what's going to happen now is that this x plus 5 and this x plus 5 can cancel out. Those terms will cancel each other, and I'm left with the 3x minus 1 in the numerator. I don't need parentheses around it anymore because it's the only thing that's left. That would be my answer. Now, a quick note, and this is important in section 1.2 where we're going to be using this stuff. This expression and this expression, if I think of them as functions of x, they are almost identical. And what I mean by that is any number I plug into this expression for x, if I plug that same number into this expression for x, I'll get the same thing, because this is basically equal to this because of this algebraic work that I did. But I say almost because there's one exception to that rule. I can't plug -5 into this expression, but I can plug -5 into this one. If I plug -5 into this expression over here, this will be dividing by 0, which we know is not allowable. But if I put a -5 into this expression, I end up with -16. I get a real number. That's no issue. So these two functions, if I think of them as functions, agree with each other for all but one value of x. In section 1.2, we'll talk about why that's relevant. But for now, that's just going to be a side note. Let's try another one. I want to look at a different type of expression that's similar to a rational expression. Rational expressions are expressions that have a polynomial in the numerator and denominator. So it creates a quotient of polynomials is how we think of that. My other examples are also going to be quotients of expressions, but none of them are going to be strictly polynomials. So technically I can't call them rational expressions, but they're close enough. So the next one I want to look at is this. Let's simplify this expression, 3 over x plus 1, and that all goes over 4 minus x. What does it mean to simplify an expression like this? Well, what we have here is something that we sometimes call a complex rational expression, which is not the same thing as the term complex number, which is like imaginary numbers. That's something you learn about in intermediate algebra. It's a different use of that word. But what we mean by complex rational expression is that we have rational expressions appearing within larger rational expressions. This 3 over x just by itself is a rational expression, but it's appearing in this larger rational right here. So what we do in these cases is we try to eliminate any of the small denominators that are appearing here. And by small, I mean like this 3 over x, this smaller rational expression within the larger one. I want to eliminate that x somehow. The trick to doing this is to multiply this entire expression by something that's equivalent to 1. In this case, what it's going to be is x over x. Remember, if I divide a number by itself, I get 1. And the reason that's important is because if I multiply something by 1, I'm not changing it. So I'm allowed to do this because I'm not actually changing anything. But the benefit of doing that, if I put these in parentheses, and if I distribute that x in here, and then there, and there, watch what happens. So when I do 3 over x times x, the x here and the x in the denominator cancel each other out, and the 3 is all that's left. Then I have 1 times x, which is just x. Down in my denominator, x times 4 would be 4x. Negative x times x is negative x squared. This would be considered simplified, the way that we're going to define that. And again, it may not be what other textbooks refer to simplified, but for us, the fact that we've eliminated any of those smaller denominators is what we're using to justify that. So now it's just a regular rational expression. Let's take a look at another problem. This one will be similar to part B, but it's a little bit more complex, a little more complicated. 1 over x plus 1 minus 3 over x minus 1. Okay? And then what I'm going to have next in my denominator is just an x plus 2. All right? So I want to do the same thing that I did in the previous problem. I want to eliminate any of the smaller denominators that are appearing in the problem. And I want to do that by multiplying by something that's equivalent to 1, just like the last example. But this one's going to look a little bit more complicated. Basically, what I'm going to do is I'm going to take every little mini denominator. I'll call them mini denominators. I'm going to take all of the mini denominators that I see in this expression and multiply them together. So x plus 1 times x minus 1. And that is going to become both my numerator and my denominator here. And the reason I'm doing that is because this would be equivalent to 1. My numerator and denominator are the same thing. But when I multiply that whole thing into both of these and here, I'm going to have something that cancels with each of these denominators. So for example, right here, if I distribute this product to this first expression here, I'm going to get x plus 1 in the denominator canceling with this x plus 1 that's being multiplied. This and this cancel. What's left is the 1 here times the x minus 1 there. So I get 1 times x minus 1. That's all that's left. Next, when I distribute this to that rational expression, this x minus 1 here is going to cancel with this x minus 1 in my denominator, leaving me with just 3 times x plus 1. But be careful to keep that minus right there. So we're going to think of that not as a 3, but really as a negative 3. Like this, okay? Down in my numerator, I have x plus 2. Then I'm multiplying that with x plus 1 times x minus 1. Notice there was no mini denominator in this bottom expression, so there was nothing that either of these would have canceled with. I'm not even going to multiply that denominator out. It might be helpful to keep it in that form, so we're just going to leave it that way. I am going to simplify the numerator, though, because I think I can combine some like terms and stuff like that. So the 1 times x minus 1 is just x minus 1. I need to distribute a negative 3 in here, which gives me negative 3x minus 3. When I simplify that, I'm still going to have this down here. Let's move up a little bit, x minus 1. Okay, now let's see what happens if I simplify this. So I have x minus negative 3x. That would be negative 2x. And then I have negative 1 minus 3. That's negative 4. Okay. X plus 1, x minus 1. The denominator is just along for the ride this whole time. It might feel like we're done at this point, but if you notice, I can factor a negative 2 out of this numerator here because I have a common factor of negative 2 up there. And what would happen if I did that? Negative 2, that would leave me with x here, and it would leave me with plus 2 there over x plus 2, x plus 1, x minus 1. And by doing that, I've revealed that there's more to do. I can cancel this new x plus 2 that's just appeared with that x plus 2 right there. And looking at what's left, I have negative 2 over x plus 1, x minus 1. And that's about as simplified as I'm going to get it. I could multiply that denominator out. It would just come out to x squared minus 1 if I did that. But I'm not worried about that. I'm going to leave it in this form because I think that's fine. Okay? So you can see this one had more steps than the previous problems, but that's also because we started with something more complicated. Let's take a look at a couple more. And these last two problems are going to involve radicals. So the first one I want to do is simplify 4 minus root x over 2 plus 3x. Now this one, it may not be immediately clear what it means to simplify this. And in fact, when we do simplify this problem, or this expression, the thing that we're going to get may not even look all that simplified. It may look more complicated. We're going to see. But the idea here is, let's not get too hung up on the word simplify. It's to basically get rid of radicals in certain places. So I want to get rid of the radical that's appearing in the numerator. I'm going to end up with a radical in the denominator, but for what I'm trying to do here, we're going to consider that to be okay. So the trick here is very similar to what we did in the last two problems really. We want to multiply by some rational expression that's equal to 1, which means the numerator and denominator will be the same thing. Now, the trick is to take a look at whatever expression has the radical in it, and we choose what's called the conjugate of that expression. The conjugate is an expression that looks almost identical to this one, but if we have a minus here, we replace it with a plus, and if we have a plus here, we replace it with a minus. So I have a minus there. I'm going to replace that with a plus. Okay? And then down here, because we want this expression to be equal to 1, we put the same thing. Why are we doing that? Well, off to the side here, I'm going to write something really important. In algebra, you learn this factoring technique. If I have a minus b times a plus b, that turns into what we call a difference of squares, a squared minus b squared. It's very easy to verify that just by multiplying this out and combining like terms. But you use this so much in algebra that you're sort of asked to memorize it, and it's really important in calculus too. So looking at this expression, I have something kind of that form over here. I have a minus b, a plus b. And I'm calling it that because the first terms are the same, 4 and 4, and the second terms are the same, root x and root x. The only difference is a minus here and a plus here, just like what I have here. So I know from this expression, this sort of technique over here, I'll box this off because this is like on the side, this is going to multiply out to the first thing squared minus the second thing squared. 4 squared is 16, minus the second thing squared. The square root of x squared is just x, right? Down in my numerator, I have 2 plus 3x times 4 plus root x. Notice what happened down here is I took this expression and multiplied it to this expression, but I didn't actually distribute anything out. I just wrote them as a product. And in fact, I'm actually going to leave it in this form. If it would help us in a problem to multiply it out, we could, but we're not looking to do that here. The important thing is that we got that radical out of the numerator. As we'll see in section 1.2 in the parent class, being able to do that will help us to solve certain limits where radicals appear. One last example, similar to this one, just slightly more complicated. I want to simplify 1 plus the square root of 1 plus x. Notice that I have a 1 plus x appearing in there. Down in my denominator, I'm going to put an x minus 10. Okay, and this is the same idea. We want to multiply this by something that's equal to 1, but would, in that process, eliminate the radical appearing in my numerator. So that's going to be the same technique. I want to look at the thing that has the radical in it, multiply by the conjugate of that thing. So that's just taking this plus and replacing it with a minus. 1 minus the square root of 1 plus x over 1 minus the square root of 1 plus x. Then once again, I have a plus b, a minus b, so I know that the product is going to be a squared minus b squared. A is 1 in this case, and 1 squared is just 1, minus b squared so b is the square root of 1 plus x. If I square it, I get rid of that radical. However, the 1 plus x that's left after doing that, I'm going to make sure that I put that in parentheses. And it's important to do that because it's a squared minus b squared here. And b squared is all of 1 plus x. If I didn't include this set of parentheses here, then basically what I'd be saying is I'm only subtracting this 1 when I do the minus step here and not the x. But by putting parentheses around it, I'm indicating that I'm subtracting the whole thing, which is what should be happening there. Down here, I'm going to have x minus 10 times 1 minus the square root of 1 plus x. And as we've been doing, we're going to leave the denominator factored because it's not going to be important for us to multiply that out. I will, however, simplify this. If I were to distribute this minus sign into both of these terms here, I'm going to get a minus 1 and a minus x. But this one minus this one is 0, which means the only thing left after all of that is just negative x. My denominator stays the same, and we're going to call it good after that. Okay, that's going to be my final answer. So that's a few examples of simplifying these rational or rational-like expressions. And once we are going through section 1.2 in the parent class, you're going to see where this is going to be really helpful in evaluating limits. But that's going to wrap things up for this week.